Welcome back, everybody. Ready to dive into some abstract algebra?
Absolutely. Always up for a challenge.
Today we're looking at Ivan Zelich's Indivisible Sequences and Descendability. Got excerpts right here.
Oh yeah, this paper's really something.
I'm ready to get my brain twisted a bit. How about you?
Let's do it. I think Zelich is onto something pretty significant here. I mean, constructing faithfully flat ring maps.
That aren't descendable, right?
Right. And he does it using this whole new idea of indivisible sequences.
So that's where we're headed. I'm already intrigued.
Okay.
We got to start with the basics. What exactly are these indivisible sequences?
Well, the paper kicks off with the idea of one indivisible sequence.
Okay, one step at a time.
It's basically you've got a set, it's denoted as S, and a map from S to a ring R written as S.
Sounds simple enough so far.
But here's the catch. This map has to be what's called R universally injective.
Wait, hold on. Are universally injective. Now we're getting into the thick of it.
Yeah, it's a bit of a mouthful.
Right.
But it basically means no matter what other ring you take, call it R, as long as there's a ring homomorphism from R to R.
Okay, I'm
The
following.
map ARS stays injective even after we tensor it with this new ring R.
So it's like a super strong version of injective. It can't lose that property even when we're working with bigger rings.
You got it. The injectivity is like rock solid.
Robust.
Yeah.
I like it. But is there another way to think about this R universal injectivity? Maybe something a little less abstract?
Definitely. The paper actually gives an equivalent condition. It says the map ARS has to be injective, that part we know.
Right.
And its co-kernel, that's like the leftover part that the map doesn't cover, has to be R flat.
Ah, flatness. We did a whole deep dive on that a while back, right? It's all about how modules behave nicely with tensor products.
You're good with your memory. And that flatness is key here. It makes sure the map behaves well even when we're in these extended rings.
Gotcha. So flatness ensures the map plays nicely in a bigger playground.
Exactly. Now, to really get this, let's look at an example from the paper. Example 2.3i, it uses polynomials.
Polynomials. Okay, I can handle that.
So we've got the ring of polynomials with coefficients in a ring K. It's written as K.
Right, KX, the classic polynomial ring.
And the map takes an element, let's call it A, from the ring K, and sends it to the polynomial X set.
Okay, I'm visualizing it. So if our ring K is the integers, this map would send the number 2 to the polynomial x2.
Exactly, you're getting it. And this map, it turns out to be Kx universally injective.
So it's a perfect example of a one indivisible sequence.
A textbook case.
Okay, I think I'm starting to wrap my head around these one indivisible sequences, but I know the paper goes a step further, right? What about these n-indivisible sequences?
Right, those are the next level. An n-indivisible sequence is basically a collection of these one indivisible sequences.
So n sets and n maps.
Exactly. Each set is denoted as psi and has its own map A, but there's an extra condition. We got to look at what happens when you take an element from each of the psis.
Okay, picking one element from each set.
Right. Then you apply their corresponding maps to get a bunch of elements in the ring R. Now, consider the ideal generated by these elements.
Ah, ideals. Those are like special subsets of a ring, right?
Right. And this condition says that ideal cannot contain the multiplicative identity of the ring.
Which means it can't be the whole ring, right?
Exactly. It's like saying those mapped elements, even combined, they don't span the whole ring algebraically.
Okay, interesting. So it's all about placing constraints on where those elements can land in R.
Precisely. Now, the paper gives us this helpful proposition 2.2. It basically shows how to build these n-indivisible sequences from the one indivisible ones.
So if we've got a good one indivisible sequence, we can use it as a building block.
Exactly. It says if you have a one indivisible sequence ARS and some other sets T1 through Tn, and the set S is at least as big as all the T's combined.
Okay, so S needs to be sufficiently large.
Then boom, you can construct an n-divisible sequence from that.
So we can bootstrap our way up to more complex sequences?
It's exact.
But why go through all this trouble? Why are these indivisible sequences so important in the grand scheme of things?
That's where it gets really exciting. These indivisible sequences, they're the key to constructing those faithfully flat ring maps that are not descendable. And the connection is through a concept called X groups.
X groups. That rings a bell. Didn't we say those measure how non-trivial certain algebraic relationships are?
You got it. And theorem 2.4 in the paper, that's where the magic happens. It links these n-divisible sequences directly to the non-vanishing of certain X groups.
Okay, break that down for me.
Basically, it says if you've got an indivisible sequence and the sets in the sequence, the size, they're big enough, each one at least the size of a Leffy minus one.
LV minus 1. We're talking about different levels of infinity here, right?
Right. Different sizes of infinite sets.
My brain's already hurting.
I know, right? But stay with me. So the theorem says if those sets are big enough, then a certain X group, specifically one associated with those sets, it won't be zero, meaning the relationship it captures is non-trivial.
Okay, so the size of the sets in our sequence has direct consequences for the complexity of the algebra involved.
You got it. The bigger the sets, the more intricate things get.
Makes sense. But how does this all tie back to descendability? You mentioned that earlier.
Right. So there's this idea of a descendability exponent tied to a ring map. It basically tells you how non-descendable that map is.
Yeah.
And theorem 2.7, it shows that if you have an n-divisible sequence, you can actually construct a faithfully flat ring map with a descendability exponent of exactly n's.
Wow, so we're not just describing these maps, we're building them with these sequences.
Exactly. It's like having a recipe for non-descendability.
Now that's power. But I'm curious about the proof of this theorem 2.4, the one that connects the indivisible sequences to the X groups. How does Zelich actually pull that off?
It's a pretty clever proof, a bit of a combination of set theory and homological algebra. The basic idea is let's assume that X group is 0, and then show that leads to a contradiction.
Classic proof by contradiction. I love that.
Oh, me too. They always feel a bit like solving a puzzle.
So what happens when we assume that X group vanishes?
Well, if it does, then we can build a very specific map.
What kind of map?
It's a map that, if it exists, would totally mess up the whole idea of our indivisible sequence. Remember that condition about the mapped elements not generating the whole ring?
Yeah, the ideal they generate can't contain the multiplicative identity.
Right, exactly. That's what this map would violate. But to show this map can't actually exist, Zelich uses a very important result from set theory. It's proposition 2.6 in the paper.
Okay, proposition 2.6. Sounds like we need to dig into that to understand the rest of the proof.
Absolutely. It's the linchpin of the whole argument.
Proposition 2.6, all right?
Yeah.
Let's crack it open and see what's inside.
So this proposition, it's all about these functions. They're denoted as vi, and there's one for each of the sets in our indivisible sequence, each of the size.
Okay, one function per set. What do these vi's do?
They take an element as input, but the catch is this element has a component from every set except the one vi is associated with.
So if vi corresponds to S2, the input has components from S1, S3, and so on, but nothing from S2.
Exactly. And the output, it's another function, but with finite support.
Ah, finite support. Those are the functions that are mostly 0, right? Except for maybe a handful of points.
You got it. Now, the purpose of these vi functions, it's like they're capturing some kind of relationship between the elements of different sets in the sequence.
Okay, so they're like little scouts, checking out how things interact across sets.
That's a good way to put it. And the proposition, it has this key condition. The sets, the size, they have to be big enough. Specifically, each side needs to have at least a Leffy minus 1 elements.
A Leffy minus 1, there's those levels of infinity again. They keep popping up.
They're essential here. It's like we need enough space within these sets to guarantee we can find a very special element.
A special element. What's so special about it?
This element, let's call it Z, it has a component from each of the sets psi. And the cool thing is if you plug A's into any of the vi functions in a specific way, the output is always 0.
Always 0. That's pretty powerful. But hold on, how do we even plug A's into vi? Didn't you say the input to vi doesn't have a component from the set psi that it's associated with?
Ah, good catch. It's a little tricky. To evaluate vi, A's, we first have to remove the component of A's that comes from psi.
So if vi corresponds to S2, we'd chop off the second component of S before plugging it in.
Exactly. It's like a little surgery on S.
Yeah.
And then the magic happens. The output of vi is guaranteed to be 0.
And that's what makes this so crucial in proving theorem 2.4, right?
Exactly. Remember how in that proof we're trying to show that assuming the X group is 0 leads to a contradiction?
Yeah, we're trying to build a map that would break the rules of our indivisible sequence.
Well, this is this special element. It lets us do exactly that. It shows that the map we construct, it would force the elements from our sequence to generate the whole ring.
And that's forbidden. The ideal they generate can't contain the identity.
Right. So it's a contradiction. And because of that, we know that initial X group can't be 0 after all. Proposition 2.6 is the key to unlocking that whole argument.
That's incredible. A set theoretic result having such a huge impact on this homological algebra problem.
I know, right? Math is full of these amazing connections. Now, remember how we were talking about how Zelich uses indivisible sequences to actually build these faithfully flat, non-descendable ring maps?
Yeah, that's what I'm really excited about. How do we go from this abstract setup to concrete examples?
Well, that's where Theorem 2.12 comes in. This theorem, it's like a blueprint for constructing these maps. And a key ingredient is the concept of a symmetric algebra.
Symmetric algebras. Now, those sound vaguely familiar, but I think I need a refresher.
Sure. Think of it this way. A symmetric algebra, it's like a machine that takes a module as input and outputs a ring.
Okay, so we're transforming modules into rings.
Precisely. It's a way of building a free commutative algebra generated by the elements of the module.
So we're taking a module, which is already a pretty rich structure, and making it even richer by turning it into a ring. And it preserves that nice commutative property.
Exactly. Now, in Theorem 2.1, Zelich takes our n-indivisible sequence and uses it to define a map. But this map is between modules. It's not between rings yet.
Okay, so we're working one level down from rings.
Right. But then he applies this magic functor. This functor, it takes a module and spits out its symmetric algebra.
So we're lifting that module map up to the level of rings.
Exactly. And the beauty is, this ring map, it inherits all the good stuff from our original indivisible sequence.
What kind of good stuff?
Well, for starters, it's faithfully flat.
Faithfully flat, one of those key properties we've been chasing.
And it has a descendability exponent of exactly just what we wanted.
Amazing. So we're using these indivisible sequences to carefully control the properties of the ring maps we create. It's like we're engineers of non-descendability.
I like that, engineers of non-descendability.
But it doesn't stop there, right?
Ooh.
The paper dives into some specific examples of these constructions.
You bet. Corollary 2.13 gives us two juicy examples. One deals with polynomial rings, something we've already touched upon, and the other ventures into the realm of Piboulian rings.
Polynomial rings, those feel a bit more comfortable. Let's start there.
Sounds good. So in this example, we have a ring R, but it's not just any ring. It's a polynomial ring in n variables over some base ring, k.
And that n, that connects back to our n-indivisible sequence, right?
Right, you are. If we're working with a 3-indivisible sequence, R would be a polynomial ring in 3 variables.
Okay, I'm picturing it.
Now, the corollary uses a specific 1-indivisible sequence to get the ball rolling. This is the one we talked about earlier, where an element a from k gets mapped to the polynomial xa.
That's our go-to example. So we take this one indivisible sequence and we build a symmetric algebra from it.
Exactly. And in this case, that symmetric algebra is a polynomial ring, but it's a polynomial ring in one variable over our original ring, R.
Whoa! So we're building a polynomial ring on top of another polynomial ring. That's like polynomial inception.
I know, right? It's polynomials all the way down. But the cool thing is, the ring map from R to this new polynomial ring, it has all the properties we want. It's faithfully flat, and it has descendability exponent n. The corollary even mentions some other nice properties, like the Kroll dimension of these rings.
Kroll dimension. Refresh my memory on that one.
Sure. It's a way of measuring the size or complexity of a ring. You can think of it as the length of chains of prime ideals in the ring.
Okay, so a bigger Kroll dimension means a more complex ring.
Roughly speaking, yeah.
Yeah.
And in this case, both our original ring R and this new polynomial ring we built, they both have Kroll dimension n.
So the Kroll dimension matches the number of variables in our polynomial rings, which also links back to the n in our indivisible sequence. It's all connected.
It's beautiful, isn't it? The corollary also mentions another property, noetherianity. Remember that one?
Vaguely. It has something to do with how ideals behave in a ring, right?
Right. A noetherian ring, it's a ring where every ideal is finitely generated. So you can't have these infinitely long ascending chains of ideals.
Okay, that makes sense. So what about noetherianity in this example?
Well, the corollary states that both rings involved are alephin minus 1 noetherian.
Alephin minus 1 noetherian. So again, we see those levels of infinity playing a role in characterizing these rings.
Exactly. It's all about the size and complexity of those sets.
Okay, so we've seen how indivisible sequences can be used to create these interesting ring maps with polynomial rings. What about the second example, the one with the p-Boolean rings?
Ah, yes, p-Boolean rings. Remember, those are rings where every element raised to the power p is equal to itself.
Right, like if p is 2, every element is its own square.
Exactly. This example, it uses a different approach than the polynomial one. It uses a special functor. It's denoted FPR. And what it does is it takes a module as input and outputs a p-Boolean ring.
Okay, so this functor lets us move from the world of modules to the world of p-Boolean rings.
You got it. And in the corollary, Zelich uses an n-indivisible sequence to first define a map, but this map is between modules.
So similar to the polynomial case, we're starting with a map at the module level.
Right. But then we apply this FPR functor, and boom, we get a map between p-Boolean rings.
So we're lifting that module map to the level of rings using this functor.
Precisely. And just like in the polynomial case, the resulting map, it's faithfully flat and has descendability exponent n. The corollary even tells us a bit about the cardinality of these p-Boolean rings.
Wow, so we've got these two different constructions, both using indivisible sequences to create faithfully flat ring maps with controlled descendability properties.
Isn't it remarkable, this one simple concept leading to such rich and diverse examples?
I'm starting to see why you're so excited about this paper. It's really groundbreaking stuff. But I have to admit, all these constructions and properties, it's a lot to keep track of.
It is. It's definitely dense material. Maybe we should take a breather here and recap the key takeaways before we delve any deeper.
That's a great idea. I think a little review would help solidify some of these concepts before we move on to the next section of the paper. Okay, back to Zelich and his indivisible sequences. Really been a fascinating exploration so far.
Yeah, seeing how he uses them to build these non-descendable ring maps, it's quite something.
And with such precision, too, controlling that descendability exponent, that's pretty remarkable.
It is. And it all comes back to those carefully chosen indivisible sequences.
Speaking of carefully chosen, I'm thinking about that set theoretic proposition, Proposition 2.6. It played such a crucial role in proving Theorem 2.4. Remember how it guaranteed the existence of that special element?
Ah, yes, Proposition 2.6. That's where the real set theoretic magic happens. It's what lets us connect those indivisible sequences to those X groups.
I'd love to unpack that proposition a bit more. Maybe revisit the statement itself and really dissect what's going on.
Sure, let's break it down. So we're dealing with these functions, denoted vi, and there's one for each of the sets psi in our indivisible sequence.
Okay, one vi per set. Got it. What do these functions do?
Well, each vi takes an element as input, but here's the catch. This element has a component from every single set in the sequence, except for psi, the one that vi is associated with.
So it's like vi is intentionally ignoring its own set.
Exactly. It's focusing on the interaction between all the other sets, and the output of vi, it's another function, but one with finite support.
Finite support meaning it's zero almost everywhere except for a finite number of points.
Right. You got it. So these vi functions, they're like little probes examining relationships between elements from different sets, but always leaving out their own set from the mix.
Interesting. So they're giving us a glimpse into how elements interact across sets, but from a very specific perspective.
That's a good way to think about it. Now the proposition has this crucial requirement. The sets psi, they have to be sufficiently large. Each one needs at least Aleph minus 1 elements.
That was Aleph numbers. They'd come back to haunt us. Always a reminder that infinity comes in different sizes.
It does. And here it's like we need enough room within these sets to guarantee that a very special element exists.
That's the element that the proposition guarantees, right? The one that makes all the vi functions vanish.
Exactly. This element, let's call S, has one component from each of the psi sets. And the amazing thing is, if you plug is into any of the vi functions in a very specific way, the output will always be 0.
Always 0. That's remarkable. But I'm still a bit confused about how we actually plug is into vi, because vi doesn't accept an element from psi, right?
Right. It's a bit subtle. To use is with vi, we have to first remove the component of is that belongs to psi. So we're essentially tailoring is to fit each vi.
So if vi is associated with the set S2, we'd remove the second component of is before using it.
Exactly. It's like we're surgically removing the part of S that V is trying to ignore, and then boom, the output is guaranteed to be 0.
And that's the key to the proof of Theorem 2.4, right?
Precisely. Remember, in that proof, we're assuming the relevant X group is 0, and we're trying to show that leads to a contradiction.
Yeah, we're trying to build a map that would break the rules of our indivisible sequence.
Right. And this special element S is what allows us to do that. It shows that the map we construct, if the X group were 0, would force the elements from our sequence to generate the entire ring.
Which would violate the defining property of the indivisible sequence. The ideal they generate can't contain the identity.
Exactly. So we reach a contradiction. That means our initial assumption that the X group is 0 has to be wrong. And all of this hinges on the existence of the special element S, guaranteed by Proposition 2.6.
That's incredible. This whole journey has been a whirlwind. We started with these indivisible sequences, explored their connection to the descendability of ring maps, dove into the intricacies of set theory, and now we're seeing how it all comes together to prove these powerful results about the structure of rings and modules.
It's a testament to the beauty and interconnectedness of mathematics, isn't it? These seemingly simple concepts leading to such profound insights.
Absolutely. Zelich's work opens up a whole new way of thinking about ring maps and their properties. I can't wait to see where this research leads in the future.
Me too. There's still so much to explore in this area.
Well, on that note, I think it's time to wrap up this deep dive. Hopefully, you've all gained a new appreciation for the elegance and power of indivisible sequences.
And for the endless surprises that mathematics holds.
Until next time, happy exploring, everyone. All right, so today we're going to be doing a deep dive, and it's going to be a deep dive into abstract algebra. Specifically, we're looking at a paper by Ivan Zelich called Indivisible Sequences and Descendability.
Oh, this is a great paper.
Yeah, so as the title suggests, we're going to be looking at a new concept called indivisible sequences, and we're going to explore its connection to descendability in ring theory. And we're hoping that we can uncover some maybe unexpected mathematical truths and maybe even challenge what we know about set theory, countability, all that good stuff. You ready to dive in?
Absolutely. Let's go.
Okay, so let's start off with this kind of intimidating sounding concept called indivisible sequences. What are they?
Okay, well, let's break it down. So first, we need to think about a ring. We can call it R. And this ring is like, the integers, but much, much more abstract. So within this ring R, an indivisible sequence is a set. We can call this set S, and there's a set theoretic map from this set to our ring R. We can call this map A. And what this map does is it assigns an element of the ring to each element in our set.
So it's creating a link between the set and the ring through this map.
Exactly. So based on this map, we construct a special R linear map, which we denote as AR. And this map is defined between a direct sum of modules over our ring R. And it's essentially a way to extend our initial map to a linear transformation that respects the ring structure.
Okay, so we're taking the map, and now we're making it essentially play nice with the rules of the ring.
Precisely. And now the definition requires this R to be R universally injective, and this basically means that no matter what ring homomorphism we apply from R to another ring, the injectivity of our map is preserved.
Okay, so the injectivity, which means that distinct elements in our starting direct sum are mapped to distinct elements in the target. That property holds strong even when we change our perspective through a ring homomorphism.
Exactly. And so this is just the very beginning. We can also define something called an n-indivisible sequence, where n is a natural number.
Okay, so how do we go from a one-indivisible sequence to an n-indivisible sequence?
Yeah, so for a one-indivisible sequence, all we needed was, one set and a map. For an n-indivisible sequence, we need n sets. So S1 to Sn, each with their own set theoretic map. To our ring R. We can denote those by O into N. And the definition requires, in addition to R being R universally injective, it requires that if we take any selection of elements, one from each of our sets, and apply the corresponding maps, the resulting elements in R do not generate the unit ideal.
Okay, so the unit ideal is that ideal that contains the multiplicative identity, which is usually 1. So it's saying that these mapped elements, even though they come from different sets, have kind of a shared limitation within the ring. They can't combine to create the entire ring through any ring operations.
Exactly.
Okay, so that's how we define it. Do you have any examples that can help us understand maybe a little bit better what we're talking about?
Absolutely, yeah. So a good example is example 2.3 in the paper. And this example uses a polynomial ring. So we can denote it by kx, where k is any commutative ring. And in this case, our set S is simply the ring k itself. And the map A takes an element A in k and maps it to the polynomial xa.
Okay, so each element in our ring k kind of transforms into a linear polynomial. But how do we know that satisfies the properties of a one-indivisible sequence?
Yeah, good question. So in the paper, they demonstrate this by showing that the co-kernel of the associated R linear map ARRS is flat. And this flatness property is very important because it's what guarantees that the map is universally injective.
Right, so that was the key requirement of the definition. So that's an example of a one-indivisible sequence, and that's specifically with a polynomial ring. What about for an n-indivisible sequence? Is there an example for that, maybe also with polynomial rings?
Yeah, so the example with polynomial rings can also be extended to an n-indivisible sequence, and that's exactly what they do in the paper. And they do that by considering a polynomial ring with multiple variables like ki1 by 2 all the way to xn. And essentially, we have a separate map for each of the variables, and it maps an element a in k to xa.
Okay, so if we were doing, like, for instance, k1 by 2, we would have one map sending it to by 1a, and then another map sending it to by 2a.
Exactly.
And then those two maps would satisfy the requirements for a two-indivisible sequence.
Yeah, and they show that this works.
Okay, cool. So we've seen an example with polynomial rings. Are there any other examples of indivisible sequences, maybe with different types of rings?
Yeah, there's another good example using rings with orthogonal idempotents. So an idempotent element E in a ring is an element that satisfies the equation EEE, and two idempotents are orthogonal if their product is 0. So if a ring R has a set of orthogonal idempotents, which we can denote as E's, where S is in some set S, then this set S can be used to construct a one-indivisible sequence. And in this case, the map S sends an element S to the ring element 1S.
Okay, so we're taking the multiplicative identity of the ring and we're subtracting the corresponding idempotent, and that forms a one-indivisible sequence.
Exactly. And they provide a proof showing that this mapping combined with the fact that the idempotents are orthogonal, will give us a ARS that is R universally injective.
Okay, so that orthogonality creates kind of a structure that's compatible with these requirements.
Yeah. And this also can be extended to an n-indivisible sequence if we consider, for example, a ring like RFPN, where FPN is a field with p elements, where p is prime and n is a natural number.
So we've now seen indivisible sequences in polynomial rings, and also with orthogonal idempotents. So they seem more prevalent than maybe I initially thought. But we don't just define indivisible sequences, we want to connect them to something called descendability. Can you explain what that is and how it connects with indivisible sequences?
Right, so descendability. Let's think about transferring properties or structures from a larger ring down to a smaller ring, maybe through a ring homomorphism. So sometimes this transfer works very smoothly, and sometimes it doesn't. And that's what descendability describes. It describes whether properties descend nicely to substructures.
So it's a measure of how well behaved this transfer of properties is.
Exactly.
And where do indivisible sequences come into all of this?
That's where things get very interesting. You can think of indivisible sequences as creating roadblocks to smooth descendability.
So their presence hinders the transfer of properties.
Exactly. And this is what they show in Theorem 2.4. They show that if you have an n-indivisible sequence within a ring, then it can actually prevent certain properties from transferring down to smaller rings.
So these indivisible sequences can actually influence how properties are transferring between rings. Can you explain a little bit more about Theorem 2.4? What kind of properties are we talking about, and how does the theorem prove this connection?
Yeah, so Theorem 2.4 focuses on a specific element in what's called an Ext group. And these Ext groups are tools in homological algebra that measure how obstructed certain extensions are. And what the theorem shows is that a particular element in this Ext group, which is constructed from our indivisible sequence, is non-zero.
And non-zero means what in this context?
It means that certain properties which are encoded in that Ext group cannot be easily transferred down.
Okay, so non-zero, that's like our red flag saying descendability is being hindered.
Precisely.
But how do we know that this element is non-zero?
Right. So the way they prove this is by contradiction. They start by assuming that the element is actually 0. And what that means is that there exists what's called an extension map that fits into a specific commutative diagram.
Commutative diagrams, those are those diagrams with arrows and objects where different paths should lead to the same result, right?
Exactly. And then what they do is they analyze this hypothetical extension map, and they manipulate it algebraically, and they arrive at a contradiction, which shows that such a map cannot exist.
So the fact that we assumed it was 0, and that leads to an impossible scenario, means that that original assumption is wrong.
Precisely.
Okay, so Theorem 2.4 established this link between indivisible sequences and descendability. But does the size of the sets in our sequence play a role?
Yes. Cardinality is very important here.
Okay, and how does cardinality come into play?
So for the conclusion of Theorem 2.4 to hold, the size of the sets in our indivisible sequence, which we denote by psi, needs to be at least n1.
Okay, so LF numbers. Those represent the cardinality of infinite sets. So LF0 is the cardinality of the natural numbers, and L1 is the next bigger infinity, and so on. So the bigger the sets in our sequence, the more powerful the roadblock they create.
Exactly. So the larger the sets, the stronger their ability to disrupt the transfer of properties. And this connection to cardinality really highlights the interplay between set theory and algebra and homological algebra.
Wow. Okay. So can we make this connection between cardinality and descendability a little bit more concrete?
Yeah.
Like, how does theorem 2.4 translate into an actual, like, more tangible algebraic statement?
Right. And that's what theorem 2.7 does. So it connects the idea of like a non-zero element in the X group to the descendability exponent of a specific ring map.
Descendability exponent, what are we measuring?
Yeah, so the descendability exponent of a ring map is basically a measure of how badly descendability fails. So a higher exponent means that certain properties are more stubborn in transferring down.
So the higher the number, the worse the descendability.
Mm-hmm.
How does theorem 2.7 actually connect that to the indivisible sequences?
Right. So what it shows is that if you have an n-indivisible sequence with sufficiently large sets, which means the sets satisfy the cardinality condition we just discussed, then you can construct a faithfully flat ring map with a descendability exponent of exactly n.
Can you remind me what faithfully flat is in this context?
Yeah, so a faithfully flat ring map is basically a special type of ring homomorphism, and it preserves certain properties when it comes to, tensor products and modules.
All right.
So make sure that the map is kind of well-behaved in a certain algebraic sense.
Okay, so we have these indivisible sequences, and we can use them to build ring maps that have a very specific descendability exponent. But why is that important? What are the implications of this finding?
Well, this gives us a very powerful tool to construct examples of rings with very specific properties. So imagine you want to study rings where descendability fails in a particular way. Theorem 2.7 gives you a recipe to construct such rings using indivisible sequences as the key ingredient.
Wow, that's pretty incredible. We're essentially engineering rings with these desired properties. This is amazing. So the paper also mentions something called corollary 2.13. What's that all about?
Right. So corollary 2.13 showcases the power of these results by constructing specific examples of ring maps with prescribed descendability exponents.
Oh, okay, interesting. So what kind of ring maps does corollary 2.13 create?
So it creates faithfully flat ring maps between what are called n1 Noetherian rings.
N1 Noetherian rings. So those are rings that satisfy a finiteness condition related to their ideals.
Okay. Yeah, Noetherian rings are very important in commutative algebra. And this corollary shows that we can find examples of faithfully flat maps between these rings that have any desired descendability exponent.
Okay, so we're not just controlling the descendability exponent, but also the type of rings involved. But before we move on, I want to go back to the proof of theorem 2.7 for a second. I'm curious about the role of proposition 2.8 in that proof.
Yeah, proposition 2.8 is very crucial. It bridges the gap between these kind of abstract statements about X groups from theorem 2.4 and the concrete statements about descendability exponents in theorem 2.7.
Okay, so how does it make that connection?
Right, so remember that theorem 2.4 tells us that a specific element in an X group, which is constructed from our indivisible sequence, is non-zero.
Right, and we want to connect that to the descendability exponent.
Exactly. So proposition 2.8 gives us the tools to make that connection, and it has two parts. Part one tells us that if a certain tensor product of extension classes is non-zero after a specific type of base change, then the original tensor product was already non-zero.
Could you remind me what base change is in this context?
Right. So base change in ring theory is like shifting perspectives. So imagine you have a ring map from A to B, and you want to study modules over B. Base change allows you to view these modules as modules over A instead.
So it's like looking at the same thing, but from a different point of view.
Exactly.
Okay.
And so part one of the proposition tells us that shifting perspectives doesn't make this non-zero property suddenly become zero. And this is important because in the proof of theorem 2.7, they're analyzing what happens to certain extension classes when we base change from a ring like RSI to a ring like SIM or SIR.
Okay, so part one helps us understand how those extension classes behave under base change. What about part two?
Right, so part two gives us a more concrete connection between the existence of non-zero elements in specific X groups and the descendability exponents of ring maps. So what it says is that assuming a specific setup with ring maps and module maps that satisfy specific conditions, similar to what we've been talking about, if a particular tensor product of extension classes is non-zero, then a corresponding tensor product related to the descendability of those ring maps is also non-zero.
Okay, so the non-zero-ness of one tensor product implies the non-zero-ness of another that is related to descendability.
Exactly. And this is crucial because it allows us to take the information about the non-zero Ext element from theorem 2.4 and translate it into a statement about the descendability exponent of our constructed ring map in theorem 2.7.
Okay, so it really is a bridge between those two.
Yeah.
Okay, so before we go too deep into those technical weeds, can we go back to the bigger picture for a second? Why are these results about descendability important?
Right, good point. It's very easy to get caught up in the details. But these findings are important because they push the boundaries of what we know about how rings behave, and they reveal that descendability, which might seem like a very natural property to have, is not always guaranteed. There are these subtle obstructions that can prevent properties from transferring smoothly between rings, and indivisible sequences give us a way to understand and control those obstructions.
So we're uncovering a new layer of complexity in the world of ring theory.
Precisely.
And this complexity has implications for other areas of math as well, right?
Yeah. So remember how theorem 2.7 allowed us to construct ring maps with specific descendability exponents? Well, corollary 2.13 takes this idea and it applies it to specific types of rings.
Right. We talked about n-one Noetherian rings. Are there other rings mentioned in corollary 2.13?
Right. They also discuss something called p-Boolean rings, and these are rings where every element, when raised to the power of p, equals itself, where p is prime. And corollary 2.13 shows that we can find faithfully flat maps between these rings that also have any desired descendability exponent.
Wow, so these results apply to more than just Noetherian rings. Okay, but before we move on, can you say more about the optimality of these results?
Right, that's a good question. So the paper does mention that the first result in corollary 2.13, the one about n-one Noetherian rings, is optimal.
Okay.
So we cannot find faithfully flat ring maps between Noetherian rings with even higher descendability exponents than the ones we already constructed.
So within the world of Noetherian rings, we've kind of hit the limit of what we can achieve using this technique. What makes that the limit?
So they relate this optimality to a known fact about Noetherian rings. Specifically, it's the fact that flat modules over Noetherian rings have a limited projective dimension.
Projective dimension.
Yeah, so you can think of projective dimension as a measure of how complex a module is. And it basically tells you how far away a module is from being projective. And projective modules are these like really nice modules. They have a lot of desirable properties.
So the lower the projective dimension, the nicer the module.
Yeah, precisely.
Right.
And for Noetherian rings, the projective dimension of flat modules cannot be arbitrarily large. It's bounded by a value determined by the Noetherianness of the ring. And so this inherent limitation on the complexity of flat modules over Noetherian rings actually subtly prevents us from constructing those ring maps with even higher descendability exponents.
Okay, so this optimality result is connected to the properties of the modules over these rings. That's fascinating. What about p-Boolean rings? Is that result optimal as well?
So the case for p-Boolean rings is a bit more nuanced. So they suggest that the result there might not be optimal in the same way.
Okay, why is that?
So it boils down to the cardinality of the p-Boolean rings that we construct using theorem 2.12. And they suggest that if we could find a way to construct p-Boolean rings with smaller cardinality while achieving the same descendability exponent, then the result would be truly optimal.
So we're looking for like the most efficient p-Boolean rings, maximizing the descendability while minimizing the cardinality.
Exactly.
Okay.
And they even mention a connection to the generalized continuum hypothesis.
Oh, the generalized continuum hypothesis. That's a big one. It says that there are no unexpectedly large infinite sets.
Exactly. It tells us that there's a very specific order and structure to the sizes of infinite sets.
Okay, so how does this hypothesis relate to our p-Boolean rings?
So if we assume this hypothesis, then they argue that we can construct these efficient p-Boolean rings.
So a set theoretic assumption has consequences for the world of algebra.
Exactly. And this highlights a really deep and often unexpected connection between different areas of mathematics.
That is fascinating. But what if we don't want to assume the generalized continuum hypothesis? Can we still get that optimal result?
That's an open question. They suggest it might be possible, but it would require new techniques.
Okay, so this opens up even more avenues for future research. It's amazing how we started with indivisible sequences, and now we're talking about, the structure of these very specific rings and even dipping our toes into set theory.
Yeah, it's pretty amazing.
This has truly been a deep dive.
It has.
I'm a little overwhelmed, but in a good way.
I know, right?
It's incredible how much we've uncovered. So what else do we have in store for this deep dive?
Okay, well, now that we've established this foundation, I think it's time to explore some more of the implications of these results for specific types of rings. We can also delve deeper into some of those open questions that we just touched upon. So stay tuned. So now that we know how these indivisible sequences can, hinder descendability, let's actually explore how they are used to construct those remarkable ring maps with specific descendability exponents. And Theorem 2.2 is where all the magic happens.
That's right. Theorem 2.12 gives us that blueprint for how we build these special ring maps. So can you walk me through that construction?
Absolutely. So the theorem starts with an n-indivisible sequence, just like the ones we defined earlier. We have, n sets each with their own mapping to our ring R.
Right. Those mappings were really important for defining indivisibility.
Precisely. So to build our ring map, we use a construction called the symmetric algebra. So for each set in our indivisible sequence, we create a symmetric algebra over the ring R. And this process builds a structure that's kind of resembles a polynomial ring, but can have infinitely many variables.
Can you remind me what a symmetric algebra looks like?
Yeah, so imagine you have a module M over a ring R. The symmetric algebra of M, which is denoted by SymRM, is essentially a polynomial ring where the variables are the elements of M.
Okay, so if, like, our module M was the set of real numbers, and it's a module over the integers, then the symmetric algebra would be like a polynomial ring with a variable for each real number.
That's a great analogy, yeah. So in our case, we apply the symmetric algebra construction to the direct sum of modules, CSR, where the size are the sets in our indivisible sequence.
So we're creating a symmetric algebra for each set in our sequence. What happens next?
So now we bring back those mappings A from our indivisible sequence. Remember that each A takes an element from the set psi and maps it to an element in our ring R.
Right. Those mappings were really key in establishing indivisibility.
Precisely. So we use those mappings to create another set of symmetric algebras, this time based on the modules R of SIR. So it's very similar to the previous one, but it includes an extra copy of R in the direct sum.
So we're creating like a parallel set of symmetric algebras, but with a slightly different module.
That's a great way to think about it, yeah. And now comes the crucial step. We combine all of the symmetric algebras that we've created using the tensor product.
The tensor product, that's a very important operation in algebra. Can you remind me what it does?
Yeah, so imagine you have two modules, M and N, over a ring R. The tensor product, denoted by M or N, basically combines these modules while respecting the ring structure, and the result is a new module that captures the interaction between the elements of M and N.
So we're like weaving together all the symmetric algebras that we created.
Exactly. And the way that we weave them is determined by the mappings A from our indivisible sequence. So those mappings guide the tensor product construction and ensure that the resulting ring map has the desired descendability exponent.
So it's like those mappings are giving the instructions for how to use the tensor product.
Yeah, that's a good visualization. And so the result of this, quite elaborate construction is a faithfully flat ring map between two rather intricate rings. And these rings are built from those symmetric algebras, and the descendability exponent of this ring map turns out to be precisely n. And this matches the n from our starting n-indivisible sequence.
That's amazing. So we started with an n-indivisible sequence. We use these symmetric algebras and tensor products, and we end up with a ring map that has the descendability exponent that we wanted. What's the intuition behind that connection? How do those indivisible sequences actually, encode the descendability exponent in all of this?
It all boils down to tension within the ring structure. So those indivisible sequences with their specific mappings and the condition about not generating the unit ideal, they create a sort of pull in different directions within the ring.
You're talking about how those mapped elements from those size sets, they can't combine to generate the whole ring.
Exactly. And so this tension is then amplified as we go through the symmetric algebra and tensor product constructions. So they kind of stretch and twist the ring structure in a way that mirrors this underlying tension.
So the indivisible sequence kind of sets up the blueprint for how this ring map should behave. And the symmetric algebras and the tensor products are the tools to make that blueprint happen.
Yeah. I like that analogy. That's a very good way to think about it.
Okay, so if we had a one indivisible sequence, we could build a ring map with descendability 1. If we had a 5 indivisible sequence, we could build a ring map with a descendability exponent of 5.
Exactly.
It's a very general result.
Yeah.
Okay, this is incredible. Are there any other ways to build these ring maps Does the paper mention any other approaches?
Yeah, actually, they do mention an alternative approach that's particularly relevant for p-Boolean rings. So remember that these are the rings where every element raised to the power of p equals itself.
Right.
And it turns out that these rings have a very close connection to those orthogonal idempotents we discussed earlier. So every p-Boolean ring can be viewed as a limit of rings that are constructed from orthogonal idempotents.
So there's a link between these idempotents and this specific type of ring.
Exactly. And so this connection actually provides an alternative method for building these ring maps with specific descendability exponents within the realm of p-Boolean rings.
Okay, I'm excited to hear more about this. How does this alternative approach work?
So instead of relying on these symmetric algebras, this approach uses a functor, which is called FPR. And this functor takes a module over a p-Boolean ring R, and it produces a p-Boolean ring.
A functor. Can you give me a quick overview of what a functor does?
Yeah, so think of a functor as like a translator between categories.
Okay.
So it takes objects and morphisms from one category and maps them to corresponding objects and morphisms in another category.
So it's like a set of rules for moving things from one mathematical context to another?
That's a great way to think about it, yeah. So in our case, this functor FPR translates modules over R into p-Boolean rings.
Okay, so we have this specialized functor for p-Boolean rings. How do we use that to build ring maps?
So we use those mappings, from our indivisible sequence, just like in theorem 2.12. However, instead of applying them within the context of symmetric algebras, we apply them within the context of the functor FPR. So we feed the functor these mappings, and it spits out a ring map between p-Boolean rings.
Okay, and what about the descendability exponent? Does this approach also give us control over that?
Yes, it does. So the descendability exponent of this ring map is determined by the n from our initial n-indivisible sequence, just like with the symmetric algebra method.
So essentially, this functor preserves that information about the descendability exponent.
Exactly.
Okay, so we have two ways to construct these unique ring maps.
Mm-hmm.
One using symmetric algebras, and the other one using this functor specifically for Potcast rings.
Precisely. And having multiple perspectives is always very valuable.
Yeah.
It allows us to understand the same concepts from different angles, and it can lead to new insights.
Right. It's fascinating how we started talking about these indivisible sequences, and we ended up exploring this whole world of descendability and ring maps and these constructions. I love how math is all interconnected.
Yeah, it's truly remarkable, and there's still so much more to explore.
Before we go too far into the exploration, can we just recap what we've discussed so far?
Yeah, a recap is always helpful.
Okay, so first we defined indivisible sequences. We distinguished between one indivisible and indivisible sequences. And we talked about how they involve these mappings from sets to a ring, and that condition about not generating the unit ideal.
Yes, and those mappings and that condition were what created that tension that ultimately influenced the descendability.
Exactly. And then we explored that surprising connection between indivisible sequences and descendability.
And theorem 2.4 showed us how those indivisible sequences can act as these roadblocks to smooth descendability.
We also talked about the importance of cardinality, how the size of those sets really matters.
Right, and then we went on to talk about constructing those ring maps with specific descendability exponents using those indivisible sequences, along with these tools like symmetric algebras and tensor products, and that was theorem 2.12.
And then we even discovered an alternative approach using that functor, FPR, specifically for p-Boolean rings.
This has truly been a deep dive.
It has. I'm a little overwhelmed. It's amazing how much we've covered.
I know, it's incredible, and I'm sure our listeners are eager to hear more.
So what else do we have in store for them? What other depths are we going to explore?
So let's explore the implications of these results for these specific types of rings. And we can also dive deeper into some of the open questions that this research raises, so stay tuned.
So we've really gone deep into defining those indivisible sequences and their connection to descendability. Now, I'm really interested to see how this plays out when we talk about specific types of rings.
Great point, yeah. Let's go back to those examples in Corollary 2.13, the ones involving Noetherian rings and p-Boolean rings. So we found out that we can actually construct those faithfully flat ring maps with those specific descendability exponents between those two types of rings.
Right, and those aren't just any rings. Noetherian rings are really important in commutative algebra, and p-Boolean rings have that property where every element becomes itself when raised to a power of p.
Exactly. And what's especially cool about the Noetherian case is that corollary 2.13 tells us this result is actually optimal for those rings. So we can't construct faithfully flat maps between Noetherian rings with even higher descendability exponents than what we got from theorem 2.12.
So we hit a limit. Why is that the limit?
Well, the paper links this optimality to a really fundamental property of Noetherian rings, the fact that flat modules over those rings have a limited projective dimension.
Okay, can you remind me what projective dimension means again?
Yeah, so think of projective dimension as a way to measure how complex a module is. It basically tells you how far a module is from being projective. And projective modules, those are like those nice modules. They have lots of desirable properties.
So the lower the projective dimension, the nicer the module.
Exactly. And for Noetherian rings, that projective dimension of flat modules, it can't be super big. There's a bound on how complex those modules can be. And that bound comes from the Noetherianness of the ring.
Okay.
So it's this inherent limitation on how complex those modules can be over Noetherian rings that sort of subtly prevents us from building those ring maps between Noetherian rings with even higher descendability exponents.
So this optimality result is actually really tied to the properties of Noetherian rings. Okay, so what about those p-Boolean rings? Is that result optimal as well? Or could we do better?
Well, the case for p-Boolean rings is a bit more subtle. They suggest that the result there might not be optimal in the same way as for the Noetherian rings.
Oh, interesting. Why is that?
Well, it all has to do with the cardinality of the p-Boolean rings that we build using theorem 2.12. Remember, cardinality is all about the size of the sets. And what they suggest is that if we could build p-Boolean rings with smaller cardinality while still getting that same descendability exponent, then we would achieve true optimality.
So we're looking for the most efficient p-Boolean rings.
Yeah, that's a great way to put it.
We want a high descendability exponent, but a small cardinality.
Exactly. And to explore this further, they even bring in the generalized continuum hypothesis from set theory.
Ooh, set theory. Now we're talking. The generalized continuum hypothesis. That basically says there's no surprisingly large infinite sets, right?
Precisely. It tells us there's a specific order to the sizes of those infinite sets.
So how does this set theory stuff connect to our p-Boolean rings?
Well, they argue that if we assume the generalized continuum hypothesis, then we can actually build those efficient p-Boolean rings we were just talking about.
Right.
And we can hit that optimal bound on the descendability exponent for a given cardinality.
So a set theory assumption can actually affect our algebra results.
It really can. It shows how interconnected math is. But it also makes you wonder, what happens if we don't assume the generalized continuum hypothesis? Can we still get that optimal result?
Yeah, that's a really interesting question.
The paper suggests that, yeah, it might be possible, but we'd need new techniques.
Okay, so more research to be done. Well, this has really opened up some interesting questions. We started with these, kind of abstract indivisible sequences, and we ended up talking about the specifics of Noetherian rings and p-Boolean rings and even set theory.
I know, right? It's pretty cool.
It's amazing how one paper can have so many different avenues for further mathematical exploration.
That's what's so great about math research. Every answer often leads to more questions.
Well said. To all our listeners out there, thanks for joining us for this deep dive. We hope you enjoyed it and maybe even got inspired to explore some of this yourself.
Absolutely. Keep those mathematical minds curious. And we'll see you next time.
Welcome back, everyone. Today, we're going to be tackling some pretty abstract algebra.
Oh, yeah.
We're diving deep into Ivan Zelich's paper,
Okay.
Indivisible Sequences and Descendability.
Sounds interesting.
It's a preprint paper, but it's making some waves in the ring theory community.
Definitely.
It really explores some fundamental concepts in ring theory.
Yeah, you're right. It digs deep into the interaction between these new things he calls indivisible sequences and the concept of descendability in faithfully flat ring maps.
Okay, so before we jump into the paper,
Yeah.
can you just remind us what a faithfully flat ring map is?
Sure. So a faithfully flat ring map is, well, it's kind of a special type of function between two rings.
Okay.
And it preserves these adherential properties that allows us to move information between rings without losing those important details.
Okay.
Kind of like a really reliable communication channel
Gotcha.
between two structures.
So Zelich's abstract makes some pretty bold claims.
It does.
He talks about constructing these faithfully flat ring maps that aren't descendable.
Right.
So what does that even mean?
So descendability in this context is about the ability to push properties or structures from one ring to another through that faithfully flat map. Like imagine we have a fact that holds true in one ring, and we want to know if that same fact is still true after we transfer it to another ring using this map.
Gotcha.
If it doesn't, then the map isn't descendable.
So he's basically saying that he can find examples where these reliable communication channels actually distort the information.
That's exactly it. And what's fascinating is that he uses these new indivisible sequences to do it.
Okay.
He's found a way to create maps that are faithfully flat, so they preserve a lot of information, but at the same time they disrupt these specific properties and prevent them from descending smoothly.
So this is where it gets really interesting. Let's dig into the introduction and see how he lays out his argument.
All right, so he starts by introducing theorems 1.1 and 1.2, which are pretty groundbreaking. Theorem 1.1 basically says, if you have a ring with a certain type of indivisible sequence, you can construct a faithfully flat map between rings of the same size, measured by their cardinality. And this map won't be descendable.
So we can construct these non-descendable maps, but why?
Yeah, so it challenges our assumptions about how faithfully flat maps behave. We typically think of them as preserving a lot of information, but Zelich work shows that they can be quite subtle and even counterintuitive.
I see. It's like we're realizing that these maps are more nuanced than we initially thought. Now, Theorem 1.2 seems to take this concept even further,
Absolutely.
It introduces this idea of a descendability exponent.
It does, yeah.
So can you unpack that a little bit?
Sure. So Theorem 1.2 shows that we can actually quantify, in a sense, how non-descendable a map is. This descendability exponent measures the complexity of the map and how much information gets lost when we try to push properties through it. And what's really fascinating is that he shows these exponents can exist even in rings with very specific finiteness properties, like being N01 Noetherian.
So it's not just that these maps exist, but we can actually measure how much they disrupt the information flow.
Exactly.
That's wild. Now, I'm really curious about these indivisible sequences. What are they and how do they fit into all of this?
Well, that's where the heart of the paper lies. In section 2, Zelich lays out the groundwork for understanding these sequences. He starts with definition 2.1, which can seem a bit technical at first glance, but it's really the foundation for everything that follows.
Let's break down definition 2.1 then. It talks about a set theoretic map from a set S to a ring R. And then using this to construct an R-linear map. What's going on there?
So he's essentially taking a simple map between a set and a ring and using it to build a more complex map between structures we call modules. These modules are like vector spaces over a ring. And the R-linear map connects them in a specific way.
And this R-linear map needs to be universally injective, right?
That means the map remains injective even when we extend our ring R to a larger ring. Think of it like zooming out and looking at the map from a broader perspective, and it still preserves distinctness. This condition is closely tied to the concept of flatness in ring theory, which essentially means the map behaves well under certain algebraic operations.
So universal injectivity ensures that our map is robust.
Precisely.
And doesn't collapse when we change our perspective.
Exactly. And that's crucial because we want to use these maps to build those intriguing non-descendable maps between rings.
Now, how do we go from this single map to a whole sequence of maps?
That's where the n-indivisible sequence comes in. Essentially, it's a collection of these universally injective maps, but with an additional constraint. The images of these maps, when considered as elements of the ring R, should not generate the unit ideal.
Hold on. Unit ideal. Can you remind us what that is?
So the unit ideal is just the entire ring itself. So saying that the images don't generate the unit ideal means there's something in the ring that can't be expressed as a combination of these images. It's like these images aren't enough to cover the entire ring.
So it's a way of ensuring that our sequence of maps has a certain level of independence.
Yeah, we want them to be distinct and capture different aspects of the ring's structure.
Now, Zelich provide some concrete examples to illustrate this concept, right?
Yes, he does. Example 2.3 is a great starting point.
Okay.
He shows how to construct a one-indivisible sequence using the familiar concept of polynomial rings.
Okay.
You take the ring of polynomials K over a field K
Mm-hmm.
and define a map that sends each element of the field to a simple linear polynomial XA.
Okay.
This seemingly simple map actually satisfies all the conditions
Okay.
to be part of a one-indivisible sequence.
So we're taking something familiar like polynomials
Right.
and showing that it can be used to build these more abstract objects.
Precisely. And this example then extends naturally to
Okay.
multivariable polynomial rings.
Yeah.
You can construct an indivisible sequence
Yeah.
using the ring k by 1 xn.
Okay.
It's a beautiful way to see how this concept generalizes.
And he hints that this connects to p-Boolean rings,
Right.
which we'll need to unpack later.
Yes, those p-Boolean rings are a fascinating class of rings
Okay.
that play a crucial role in this theory.
Right.
But before we get there, let's focus on Theorem 2.4, which establishes a crucial property of these n-indivisible sequences.
Okay, what does Theorem 2.4 tell us?
So it states that if we have an n-indivisible sequence,
Okay.
and the sets city involved are large enough,
Right.
and by large enough we mean they have a cardinality of
Yeah.
at least Alefi 1,
Right.
then a certain X class associated with this sequence
Mm-hmm.
is non-zero.
Now, those X classes sound pretty intimidating.
They can be.
What are they all about?
So think of X classes as tools from homological algebra
Okay.
that measure obstructions
Mm-hmm.
or twists within these algebraic structures. They're like mathematical probes
Yeah.
that tell us how entangled certain modules are.
Okay.
In this case, a non-vanishing X class tells us that our sequence is twisted enough
Okay.
to prevent certain properties from descending smoothly.
Okay, so it's like these X classes are indicators of complexity.
Right.
And Theorem 2.4 tells us that indivisible sequences,
Exactly.
under the right conditions,
Yeah.
create enough complexity
Yeah.
to disrupt descendability.
That's right. And Lemma 2.5 provides a technical tool
Okay.
to actually prove that these X classes are non-zero. It gets a bit deep into homological algebra, but the key takeaway is that
Yeah.
it solidifies the connection between indivisible sequences
Right.
and this obstruction to descendability.
That makes sense. It's reassuring to know.
Yeah.
There's a rigorous mathematical basis for this connection.
Right.
Now, how do we go from this abstract property
Okay.
to concrete consequences for faithfully flat maps?
That's where Theorem 2.7 comes in.
Okay.
It bridges the gap between the abstract properties of indivisible sequences
Mm-hmm.
and the descendability exponent of faithfully flat maps.
Okay.
Essentially, it shows that we can use these sequences
Yeah.
to construct faithfully flat maps with a specific descendability exponent.
So we're going from abstract X classes
Yeah,
to the tangible concept of descendability exponent.
right. Theorem 2.7 establishes a direct link
Okay.
between the non-vanishing X classes from Theorem 2.4 and the descendability exponent.
Okay.
It shows that if these X classes are non-zero,
Right.
then the corresponding faithfully flat map
Yeah.
will have a descendability exponent of at least in the...
So we're using the complexity
Right.
measured by the X classes
Exactly.
to control the non-descendability of the map.
That's brilliant.
That's brilliant. And Proposition 2.8 seems to provide some technical support
It does.
for this construction, right?
Yeah. Proposition 2.8 establishes some key relationships between different
Yeah.
algebraic concepts that are needed
Okay.
to make the proof of Theorem 2.7 work.
Gotcha.
It's a technical result, but it demonstrates the interplay between these abstract properties
Okay.
and the concrete consequences in this theory.
This is starting to paint a really fascinating picture.
It is.
We're using these carefully constructed indivisible sequences
Right.
to create maps that are faithfully flat, but also disrupt the flow of information in a very specific way
I love that analogy. It really captures the essence. Yeah.
of what Zelich is doing.
It does. It feels like we're playing with the fabric
Yeah,
of
yeah.
algebraic structures.
It does.
Now, let's talk about those p-Boolean rings.
Okay.
They've been popping up here and there,
They have.
and I'm curious to know more about their role in all of this.
All right. Well, definition 2.9 formally introduces them.
Okay.
A p-Boolean ring is a ring where every element raised to the power p,
Okay.
where p is a prime number, equals itself.
Okay.
They have this unique structure
Right.
and are connected to these indivisible sequences in a surprising way.
So they have this interesting property of resetting themselves
Right.
when raised to the power p.
Exactly.
But how do they fit into the larger picture of
Okay.
indivisible sequences and faithfully flat maps?
So that's where Theorem 2.0 and Proposition 2.11 come into play.
Okay.
Theorem 2.1 provides a powerful way to construct p-Boolean rings from simpler building blocks called modules.
Okay.
Like we're taking these modules
Right.
and weaving them together.
Right.
Yeah.
To create these special rings.
Okay, so we can build these p-Boolean rings.
Right.
But where's the connection to the maps
Okay,
we've been talking about?
So that's what Proposition 2.11 reveals.
Okay.
It shows that if we have a particular type of injective map between flat modules,
Yeah.
we can use it to construct a faithfully flat map
Okay.
between p-Boolean rings.
Right.
And guess what? This construction is directly linked to our indivisible sequences.
Ah, okay, so that's the connection.
It is.
We build these special rings, connect them to our indivisible sequences,
Yeah.
and then use those to create these unusual, faithfully flat maps.
Right.
It's like a chain reaction of mathematical brilliance.
You got it. It's a beautiful example of how different concepts in algebra can be woven together
Yeah.
to create something truly unexpected and profound.
This brings us to the grand finale of this section, doesn't it?
It does.
Theorem 2.12 seems to be the culmination of all this work.
You're absolutely right. Theorem 2.12 brings everything together. It states that if we have an indivisible sequence with large enough sets,
Right.
then we can construct faithfully flat ring maps
Okay.
with a specific descendability exponent.
All right.
And this construction works for both general rings and those special p-Boolean rings.
Wow. It's like Zelich has given us a master key
He has.
to unlock a whole new world of ring maps
Yeah.
with specific descendability properties.
It's a testament to the power of this theory and the depth of his insights.
And to top it all off, we have Corollary 2.13,
Right.
which seems to make the implications of this theory even more concrete.
Absolutely. Corollary 2.13 shows that these non-descendable maps with specific exponents aren't just theoretical curiosities,
Right.
but they actually exist in abundance
Yeah.
within certain classes of rings,
Okay.
like N1 Noetherian rings, and of course, Paboulian rings.
So it's not just that we can construct these maps in some abstract sense, but they're actually out there.
They are lurking within
Yes.
familiar structures like N1 Noetherian rings and Paboulian rings.
Exactly. It's a truly remarkable discovery.
I think we've covered a lot of ground here.
We have.
We started with the basics of faithfully flat maps and dove deep into the world of indivisible sequences, X classes, and these fascinating Boolean rings.
Right.
It's a lot to process.
It certainly is, but I think the journey is worth it.
Yeah.
We've uncovered some hidden gems in ring theory and gained a deeper appreciation for the power of these seemingly abstract concepts.
Absolutely. Welcome back. I don't know about you, but I'm still wrapping my head around all the intricacies of these indivisible sequences and their impact on descendability.
Definitely a lot to absorb.
Yeah.
But that's the beauty of a deep dive like this. We get to really explore the nuances of a concept.
Right.
And appreciate the depth of mathematical thought behind it.
Absolutely. Now, before we dive into the technical details of the proofs,
I think it would be helpful to just step back and reflect on the bigger picture. You know, what are the key takeaways from this paper? And why should our listeners care about these seemingly abstract results?
That's a great point. It's easy to get lost in the technicalities. But the real beauty of mathematics lies in its connections to the broader world of ideas. One of the most significant takeaways from Zelich's work is that it challenges our assumptions about faithfully flat maps.
Okay.
We often think of them as preserving information flawlessly, but his work shows that they can be more subtle and even counterintuitive.
Right. It's like we've discovered a hidden flaw in a tool we thought was perfect.
Exactly. And this has implications for various areas of mathematics that rely on ring theory, like algebraic geometry and number theory. These fields often use faithfully flat maps to study these complex objects. So understanding the limits of their descendability is crucial.
So it's not just a theoretical curiosity.
No.
It actually impacts how we approach problems in other areas of math.
Absolutely. Zelich's work is forcing mathematicians to re-examine some of their fundamental assumptions and tools.
Wow.
It's like shaking the foundations of a building to make sure it's truly stable.
I love that analogy.
Yeah.
It really highlights the potential impact
It does.
of this research.
Yep.
Yeah.
Now, another thing that struck me is the elegance of Zelich's approach.
Mm-hmm.
He introduces this concept of indivisible sequences, which at first seems quite abstract and disconnected from the problem of descendability.
You're right. It's like he pulled this new tool out of thin air, and it turns out to be exactly what's needed to unlock these hidden secrets about ring maps.
Exactly. Yeah. And then step by step, he builds a bridge between these abstract sequences and concrete algebraic results.
He does.
Theorem 2.4 establishes that crucial property of indivisible sequences, relating them to those intriguing X classes we discussed earlier.
Yes, and it's worth noting that those X classes themselves are fascinating objects.
Okay.
They come from the realm of homological algebra, which is a way of studying algebraic structures by looking at their holes or gaps.
Right.
In this case, those non-vanishing X classes are like signposts, pointing to the twists or obstructions created by these indivisible sequences.
It's amazing how these different areas of mathematics,
I know,
like set theory, homological algebra, and ring theory, all come together in this paper.
That's the beauty of mathematics. It's all interconnected. And often the most surprising discoveries arise from these unexpected connections between seemingly disparate fields.
Now, speaking of connections, I'm curious to know more about those p-Boolean rings. They seem to play a special role in this story.
They do. Remember, p-Boolean rings have that unique property where every element raised to the power p equals itself. They have a very specific structure that makes them particularly well-suited for exploring the consequences of Zelich's theory.
And Zelich provides tools to construct them, right?
Yes, he does. Theorem 2.n gives us a way to build these p-Boolean rings from simpler modules. It's like we have a recipe for creating these special rings with the desired properties.
And then proposition 2.11 links them to indivisible sequences.
It does.
And faithfully flat maps.
Exactly. Proposition 2.11 shows that a certain type of injective map between flat modules can be used to construct a faithfully flat map between p-Boolean rings. And crucially, this construction is directly tied to indivisible sequences. They're the key to making this connection.
It's amazing how these pieces fit together so seamlessly.
It is.
Now, before we dive into the proof of Theorem 2.4, which I know it's a bit intricate, can you give us a roadmap for where we're headed in the rest of the paper?
Of course. So in the remaining sections, Zelich delves deeper into the properties of indivisible sequences and explores their connections to various concepts in ring theory. He examines different notions of dimension and finiteness and shows how those concepts interact with the descendability of faithfully flat maps.
So it's like he's building upon the foundation he's laid.
Exactly.
And exploring the broader landscape of this theory.
Precisely, he shows that these indivisible sequences are not just a tool for constructing counterexamples, but they actually shed light on some fundamental aspects of ring theory.
I think we're ready to tackle the proof of Theorem 2.4. It's the heart of the paper, establishing that crucial connection between indivisible sequences and those non-vanishing X classes.
Let's dive in. As you mentioned, the proof is a bit intricate, but it's a beautiful example of mathematical reasoning. It starts by assuming, for the sake of contradiction,
that the X class we're interested in is actually 0.
So it's a proof by contradiction.
Exactly.
We assume the opposite of what we want to prove. And then show that it leads to a logical absurdity.
Classic.
Now, if this X class were 0, it would imply the existence of a specific map that fits into a certain diagram of modules and homomorphisms. This map would need to satisfy certain compatibility conditions. Essentially gluing different parts of the diagram together. In a consistent way.
So it's like we're assuming the existence of a missing piece.
Precisely.
That would make the puzzle complete.
But here's where the cleverness comes in. Zelich carefully analyzes the properties of this hypothetical map, focusing on how it interacts with specific elements of modules involved.
And I'm guessing this analysis leads to a contradiction.
He uses a set theoretic result, proposition 2.6, which guarantees the existence of certain elements in a product of sets. If those sets are large enough, These elements, when plugged into our hypothetical map,
Yeah.
force it to violate the compatibility conditions
Okay.
we assumed it satisfied.
So it's like those specific elements break the hypothetical map,
Exactly.
showing that it couldn't have existed in the first place.
It's a beautiful example of how set theoretic reasoning can be used
Wow.
to derive a contradiction in a seemingly unrelated area of mathematics.
Right.
And this contradiction forces us to conclude
Yeah.
that our initial assumption that the X class is 0 must be false.
Ah, the classic proof by contradiction.
Right.
It's like we've built a logical trap
We have.
and shown that our initial assumption leads us straight into it.
And this means the X class must be non-zero, as Theorem 2.4 states.
Right.
It's a powerful result that demonstrates the inherent complexity
Yeah.
of these indivisible sequences and their ability to create twists
Right.
in the structure of rings.
It's truly remarkable how Zelich weaves together these different strands of mathematical thought
Yeah.
to arrive at such a profound conclusion.
I agree. It's a testament to the power of mathematical thinking and the beauty of uncovering hidden connections between seemingly disparate concepts.
I think our listeners are ready for another breather
Probably.
after that intricate journey
Yeah.
through the proof of Theorem 2.4.
It was a lot.
We'll be back in a moment to explore the rest of Zelich's fascinating work. Welcome back to our deep dive. That proof of Theorem 2.4 was quite a journey, wasn't it?
It really was.
It's amazing how Zelich uses a set theoretic argument
I know, right?
to establish this crucial connection
Yeah.
between indivisible sequences and those non-vanishing X classes.
It's a testament to the interconnectedness of mathematics.
Absolutely.
Sometimes the key to solving a problem in one area lies in a seemingly unrelated field.
Now let's shift our focus to Theorem 2.7.
Okay.
It seems to be the bridge between those abstract X classes
It is.
and the concrete consequences for the descendability exponent
Right.
of faithfully flat maps.
You're exactly right. Theorem 2.7 provides a recipe for constructing faithfully flat ring maps
Okay.
with specific descendability exponents using these indivisible sequences.
Okay.
We're essentially taking that abstract blueprint from Theorem 2.4
Right.
and using it to build actual mathematical objects with the properties we want.
That's a powerful idea.
Mm-hmm.
So if I understand correctly,
Yeah.
Theorem 2.7 states that if we have an indivisible sequence that meets certain conditions,
Mm-hmm.
we can construct a faithfully flat map using that sequence.
Right.
And that map will have a descendability exponent of at least n degree.
Precisely. It's like we're choosing the ingredients, the indivisible sequences,
Yeah.
to control the flavor of the final product,
Yeah.
the descendability exponent of the map.
I see. And Proposition 2.8 provides some of the technical tools
It does.
to make this construction work, right?
Yeah, it's like the kitchen utensils we need
Right,
to
exactly.
prepare this mathematical dish.
So Proposition 2.8 establishes some key relationships
Mm-hmm.
between different algebraic concepts
Mm-hmm.
that are essential for the proof of Theorem 2.7 to work.
Right. It deals with things like base change
Okay.
and how those X classes behave under certain operations. It's a bit technical, but it
Yeah.
lays the groundwork for the main result.
Got it. So together, Theorem 2.7 and Proposition 2.8 connect
Yes.
the abstract properties of those indivisible sequences
Mm-hmm.
to the concrete behavior of faithfully flat maps and their descendability exponent.
Exactly.
We're translating from one mathematical language to another.
I like that analogy.
Okay.
Now let's bring those p-Boolean rings back into the spotlight.
Okay.
Remember, they have that unique property where every element raised to the power p equals itself.
Right. It's like they have a built-in reset button.
Exactly.
They play a significant role in the later part of Zelich's work, don't they?
They do. Theorem 2.9 provides a powerful way to construct these p-Boolean rings
Okay.
from simpler building blocks called modules.
Mm-hmm.
It's like we have a set of instructions for assembling these special rings.
So we can build them, but how do we connect them back to indivisible sequences
Right.
and those faithfully flat maps we've been discussing?
That's where Proposition 2.11 comes in.
Okay.
This proposition shows that if we have a specific type of injective map between flat modules,
Right.
we can use it to create a faithfully flat map between Boolean rings.
Okay.
And here's the crucial part. This construction is directly linked to our indivisible sequences.
Right.
They're the key to making this connection.
So it all comes together.
It does.
We build these special rings using Theorem 2.0, link them to indivisible sequences using Proposition 2.11,
Yep.
and then apply Theorem 2.7 to create those non-descendable, faithfully flat maps.
Yes.
with specific descendability exponents.
It's a brilliant chain of reasoning.
It really is, and it all culminates in Theorem 2.1 on.
Yes, it does.
This theorem states that given an indivisible sequence with sufficiently large sets,
Right.
we can construct a faithfully flat ring map with a specific descendability exponent. And this construction works for both general rings and those fascinating Boolean rings.
Exactly.
It's remarkable how Zelich ties all these concepts together.
It is.
Indivisible sequences, X-classes, P-Boolean rings, and descendability exponents.
It's really quite elegant.
He's given us a powerful framework
He has.
for understanding the subtle behavior of faithfully flat maps.
I completely agree. And the implications go even further.
Okay.
Corollary 2.13 shows that these non-descendable maps with specific exponents aren't just theoretical curiosities.
Right.
They actually exist in abundance within certain classes of rings,
Okay.
like Ono-Noetherian rings and, of course, Boolean rings.
So we've gone from this seemingly simple question
We have.
about the descendability of faithfully flat maps
Right.
to uncovering a rich tapestry of mathematical structures
Yes.
with surprising properties.
Exactly. Zelich's paper is a beautiful example of how mathematical exploration can lead to
Yeah,
unexpected and profound discoveries.
it really is.
He started with the simple question and ended up revealing a whole new layer of complexity in the world of rings.
Well, that concludes our deep dive into Ivan Zelich's Indivisible Sequences and Descendability.
It's been a pleasure.
It's been quite a journey, filled with abstract concepts, intricate proofs,
It had.
and surprising connections.
Absolutely.
I hope our listeners have gained a deeper appreciation for the beauty and depth of ring theory
Me too.
and the power of mathematical reasoning.
It's really quite fascinating.
It is. Until next time, keep exploring, keep questioning, and keep diving deep into the fascinating world of mathematics. Welcome to the Deep Dive. Today, we're going deep into abstract algebra, looking at a paper by Ivan Zelich about indivisible sequences and descendability.
It's a really cool area of research. It basically looks at how some algebraic structures behave under certain transformations.
All right, so we've got Zelich's paper here, and I have to say, some of this looks pretty intense. That's why you're here, to be our guide through this mathematical jungle.
Happy to be your guide. So basically what Zelich is doing in this paper is he introduces this idea, this concept of indivisible sequences, and shows how they can be used to create these faithfully flat ring maps that have some very interesting properties, especially when it comes to descendability.
Right. Indivisible sequences, faithfully flat ring maps, descendability. Those are the key words of the day.
Yeah, exactly. And while those terms might sound kind of scary, the ideas behind them are actually pretty elegant. Let's start with those indivisible sequences. So imagine you have a set and a map from that set into a ring. Zelich calls this sequence one indivisible if no matter what ring you're using, this map always stays injective after we apply a certain transformation that he defines.
So it's about keeping that one-to-one correspondence, making sure that different elements in the set stay distinct even as we change the algebraic context.
Precisely. And Zelich gives this really neat equivalent condition for this property. He shows that it basically boils down to two things. The map itself needs to be injective, and something called its co-kernel needs to be flat.
Okay, co-kernel, flat. Could you break those down for us a bit? The co-kernel, if I remember right, is like what's left over after we apply our map. And flat, well, that's a whole other thing.
Yeah, you're exactly right about the co-kernel. It's basically capturing what's outside the image of the map. And flatness, in this context, it means that the co-kernel behaves well under tensor products. It's a way of combining modules that respects their underlying structure.
Okay, got it. So flat modules are like the well-behaved ones in algebra. But Zelich doesn't just leave us with these abstract definitions, right? He gives us an actual example of a one indivisible sequence.
He does. He takes a commutative ring, let's call it K, and he looks at the map that sends each element A in K to the polynomial XA in the polynomial ring Ks. It's a simple shift, but it turns out to be a one indivisible sequence.
Interesting. So by shifting that variable X by each element in the ring, we create this map that satisfies those injectivity and flatness conditions. It's like this neat little algebraic dance.
Yeah, I like that analogy. And from these one indivisible sequences, Zelich builds what he calls n-indivisible sequences. And n can be any natural number or even infinity.
Okay, so things are getting a bit more complex. How do we jump from a one indivisible sequence to an n indivisible one?
So imagine you're taking n different one indivisible sequences. Now we have to make sure that the images of these sequences in our ring don't generate the unit ideal. The unit ideal is the one that contains that multiplicative identity. Usually we call it 1.
So we're putting a limit on how these images interact within the ring.
Yeah.
But why is that important? What's the purpose of avoiding the unit ideal?
It's about maintaining a certain level of complexity, or you could say non-triviality. If those images did end up generating the unit ideal, the structure would become too simple, and it wouldn't have that behavior that Zelich is trying to explore, especially when it comes to descendability.
Got it. So by avoiding that unit ideal, we're making sure these indivisible sequences have enough, oomph to be interesting. And Zelich gives us some real-world examples of these sequences, right?
He does. He shows how to make indivisible sequences using polynomial rings and also something called p-Boolean rings. In the polynomial ring example, we start with a base ring, k, and then we take the map that sends each element a to this polynomial x1 a n in the polynomial ring k n x rim.
Okay, I think I see a pattern forming here. We're shifting every variable in the polynomial by the same element from the base ring. And this, it turns out, makes an n-indivisible sequence.
Exactly. And Zelich very carefully explains why this satisfies every condition: injectivity, flatness, and avoiding that unit ideal. It's a great example of how these seemingly simple operations can create these complex algebraic structures.
I'm really starting to appreciate the detail and creativity that goes into building these sequences. But Zelich doesn't stop there, does he? These indivisible sequences, they're just the beginning.
You're right. They play a really big part in one of his central theorems in the paper, Theorem 2.4. It deals with this thing called an extend class. It's a tool used to study extensions of modules in homological algebra.
Okay, extend classes, those sound pretty abstract. Can you give us a sense of what those represent, and why is Theorem 2.4 so important?
So extend classes capture info about how modules can be extended by other modules. It's like, think of it as understanding how to glue these algebraic building blocks together. And Theorem 2.4 says if you have an n-indivisible sequence with certain size constraints, then a specific extend class that's associated with this sequence has to be non-zero.
Non-zero, meaning that it has some substance. It's not just fading into the background.
Yeah.
But proving something doesn't exist or isn't zero, that can be tricky. How does Zelich approach that?
Yeah, he uses a cool combination of techniques. He starts with the reduction step using lemma 2.5 to simplify the problem. Then he goes for this classic strategy, proof by contradiction. He assumes that extend class is 0, and then he shows that assumption creates a contradiction. So we're forced to conclude that it can't be 0.
So by assuming the opposite of what he's trying to prove, he finds this logical flaw that validates his claim. That's pretty neat. But why is it such a big deal that that extend class isn't 0?
Because it has some pretty deep consequences for understanding how descendable those ring maps are, the ones built from these n-indivisible sequences. And that brings us to Theorem 2.7. It connects those abstract extending classes to the actual behavior of those ring maps.
Okay, I'm getting the feeling that we're building up to something big here. Tell me more about Theorem 2.7 and how it relates to descendability.
Theorem 2.7 says that if you have an n-indivisible sequence, and it meets certain conditions, then you can build a faithfully flat ring map from it. And this map is going to have a descendability exponent of exactly n.
So we're not just saying the descent breaks down, we're specifying exactly where it breaks down.
Yeah.
And this is all because that extend class we were talking about isn't 0.
Exactly. It all ties together really nicely. And to prove the theorem, Zelich uses another proposition, proposition 2.8. It really digs into those tensor products and faithfully flat maps. It's like setting the stage for the big finish.
I am ready for that big finish. But before we move on, let's take a moment to appreciate how far we've come. We've gone from these simple-sounding one-indivisible sequences to these powerful theorems about descendability. It's amazing how everything is connected.
It really is. And the best part is, we're just getting started. There's so much more to discover in this paper.
I can't wait. Let's dive into part 2 and see where Zelich takes us next.
Okay, so picking up where we left off, let's look a little closer at proposition 2.8. It's really important for connecting those extend classes with the way faithfully flat maps actually behave. It's kind of like a bridge between two different areas of math.
All right, I'm ready to cross that bridge. What does this proposition tell us?
Well, there are two parts to proposition 2.8. The first one deals with derived categories. They're a way of extending the idea of modules and homomorphisms, making them a bit more sophisticated. This part tells us the conditions where certain tensor products of extensions will stay non-zero.
So it's kind of like a quality control check. We want to make sure we don't lose important info as we move between those different algebraic structures, right?
Exactly. It's about keeping things, non-trivial. The second part of 2.8 looks at faithfully flat maps and injective maps of modules. It gives us conditions where certain combinations of these maps will stay non-zero.
Okay, so we're setting things up carefully, making sure our tools can handle all these complicated constructions. And with all that in place, we're ready for Theorem 2.7, right?
Exactly. Theorem 2.7 is where it all comes together. Remember how we were talking about the descendability exponent of a faithfully flat ring map? Well, this theorem says that under certain conditions, if we start with an n-indivisible sequence, and then we build a faithfully flat ring map from it, we can be sure that map will have a descendability exponent of n.
So we're not just saying that the descent breaks down, we're saying exactly where it breaks down. And this is all thanks to those Exene classes and Proposition 2.8.
It's like we can control exactly where these ring maps break with amazing accuracy.
Wow. It's like we've climbed to the top of a mountain, and now we can see the whole mathematical landscape laid out in front of us. But Zelich doesn't stop there, does he? There's more in this paper to explore, right?
You're absolutely right. We still have more to go. And now we're going to dive into the world of p-Boolean rings and monadic forgetful functors.
Okay, p-Boolean rings. Those sound kind of, well, exotic. What exactly are they?
So imagine a ring where every element, when you raise it to the power of p, just loops back to itself. It's like a mathematical reset button.
I like that. Like a game where no matter how many times you do something, you always end up back where you started.
Exactly. And these p-Boolean rings, they're really closely connected to another concept that Zelich introduces, monadic forgetful functors. Remember we talked about functors being maps between categories that preserve structure? Well, these specific functors, they link p-Boolean rings to the world of modules and algebras over a p-Boolean ring. It's kind of like translating between different mathematical languages, but keeping the underlying meaning the same.
So we're building connections between different areas of algebra. But how do these functors tie into our discussion about descendability?
They're crucial for understanding Proposition 2.11, which sets the stage for Zelich's main result. This proposition basically says that if you have an injective map between flat modules, remember those well-behaved flat modules, and you apply certain algebraic things to it, like the symmetric algebra or the functor FPR, you're going to get faithfully flat maps between algebras or p-Boolean rings.
So we're taking a simple map and turning it into something way more powerful and structured.
Exactly. And Proposition 2.11, together with Theorem 2.7, brings us to the climax of Zelich's paper, Theorem 2.12.
Okay, let's hear it. What does this theorem tell us?
All right, so Theorem 2.12 says that if you have an n-indivisible sequence with certain properties, we can create these faithfully flat ring maps using those constructions we just talked about, and they'll have a descendability exponent of exactly n. And this is true whether we're talking about algebras or p-Boolean rings.
Wow. It feels like we've come full circle. Starting with those indivisible sequences, we explored how they're connected to those extant classes. And now we see how they actually control the descendability of ring maps. It really shows how interconnected math can be.
It really does. And the way Zelich proves Theorem 2.12 is beautiful. It brings together all the ideas from Proposition 2.11 and Theorem 2.7. It just shows how elegant mathematical reasoning can be.
I'm really impressed with how deep and complex Zelich's work is. But he doesn't stop there, does he? He keeps going and explores the consequences of this theorem.
You're right. He continues his exploration in Corollary 2.13, which demonstrates that there are faithfully flat ring maps with specific properties for any natural number n, including infinity. It really expands on Theorem 2.12.
So we're not just talking about a few isolated examples.
Yeah.
This result has really broad implications across different types of rings and descendability levels. It's like Zelich opened a door to a whole new world of algebraic possibilities.
I love that analogy. And to finish proving this corollary, Zelich brings in Claim 2.14. It looks at how to construct Peirdian rings with specific properties. It's like making sure we have all the right ingredients to bake our mathematical cake.
That attention to detail is really impressive. It's clear that Zelich has been super thorough in building his arguments and looking at all the little details of this topic.
Absolutely. And finally, to give credit where it's due, Zelich provides a list of references. He highlights the work of other mathematicians and shows how collaborative research can be. Even the most groundbreaking discoveries often build on the work of others.
It's a good reminder that knowledge is something we build together. It's a shared effort to understand how everything works.
Beautifully said. Well, it looks like we've reached the end of part 2 of our exploration of Zelich's paper. Are you ready for the final part of our journey?
I am definitely ready to see what insights and surprises await us in part 3. Let's dive in. Okay, so here we are. Back for the final part of our deep dive into Ivan Zelich's paper on indivisible sequences and descendability. It's been quite a journey so far. We've looked at all these complex algebraic structures. We've seen how they're related to those extant classes and how they affect how faithfully flat ring maps behave.
It really has been a fascinating exploration, and in this last part, we're going right to the core of Zelich's work. He's going to show us his main results, and we'll see the real power of those indivisible sequences.
I'm excited to see how it all comes together. But before we jump into that, let's just quickly go over those Paboulian rings and those monadic forgetful functors again. They're pretty important here, right?
Absolutely. Remember, a Paboulian ring is like a ring with a reset button where every element, when it's raised to the power of Pikukki, loops back to itself. And those monadic forgetful functors, they're like translators, helping us move between the world of Paboulian rings and the world of modules and algebras over those rings.
Right, like we're switching between different mathematical languages, but the core meaning stays the same. And these functors are key to understanding proposition 2.11, which is really the foundation for Zelich's main result.
Exactly. Proposition 2.11 basically tells us that if you start with an injective map that behaves nicely, one between flat modules, and remember those flat modules are the well-behaved ones in algebra, and we use certain algebraic constructions on it, like the symmetric algebra or the functor FPR, we end up with faithfully flat maps between either algebras or P-Boolean rings.
So we're taking this relatively simple map and turning it into something a lot more powerful and structured. It's like, like alchemy, turning lead into gold.
I like that analogy. And it's this kind of alchemy that lets Zelich come up with his main finding about descendability, which he presents in Theorem 2.12.
All right, drum roll, please. What does this big theorem tell us?
Okay, so Theorem 2.12 says that if you have an n-indivisible sequence with certain properties, we can use those algebraic constructions we've been talking about to build faithfully flat ring maps. And these maps, they will have a descendability exponent of exactly n. It doesn't matter if we're dealing with algebras or P-Boolean rings.
Wow, so from these kind of abstract indivisible sequences, we can actually make ring maps where the descent breaks down at a specific point. Like, we're in control of where those maps break with, like, incredible accuracy.
It's a really amazing result, and the proof is beautiful. It ties together everything we've been talking about, the characteristics of n-indivisible sequences, those extant classes, proposition 2.8, and even those P-Boolean rings and functors. It really shows how powerful mathematical reasoning can be and how elegantly all these concepts are connected.
It really is amazing. It makes me wonder, what are the implications of this theorem? Does Zelich go into that in the paper?
He does. In Corollary 2.13, he shows us that Theorem 2.12 isn't just some random result. It has big implications for understanding if faithfully flat ring maps with specific properties exist for any natural number n, even for infinity.
So it's not just a few examples. It's a general principle that works across a whole bunch of algebraic structures. That's incredible.
It is. And to wrap up the proof of this corollary, Zelich introduces Claim 2.14, which focuses on how to actually build P-Boolean rings with certain properties. It's like he's making sure we have the right tools in our mathematical toolbox.
I'm really impressed with how careful Zelich is about making sure his arguments are solid and complete. It shows how detail-oriented and precise math research really is.
Absolutely. And to wrap things up, Zelich provides a list of references. He's acknowledging the work of other mathematicians, showing how collaborative this field is. Even the most groundbreaking discoveries usually build on what others have done before.
It's a great reminder that knowledge is something we build together. We're all working to understand the world around us.
Well said. And with that, we've reached the end of our deep dive into Ivan Zelich's paper.
What an amazing journey. We started with those indivisible sequences that seem so abstract, and we ended up exploring how descendability works in ring maps. To be honest, I was a little intimidated at first by all the technical terms and complex ideas, but thanks to you, it's been a really rewarding experience.
I'm so glad to hear that. It's always exciting for me to share my love for math and to see how these ideas that might seem obscure at first can spark curiosity and a sense of wonder.
Absolutely. And for our listeners, I hope this deep dive gave you a little glimpse into the beauty and power of abstract algebra. Even if you're not a mathematician, there's something really satisfying about seeing how these intricate structures fit together and how logic and reasoning can help us uncover these profound truths about the mathematical universe.
Couldn't agree more. There are so many hidden gems in the world of math just waiting to be discovered. Sometimes all it takes is a little bit of curiosity and a willingness to explore.
Beautifully said. Thanks for joining us on the deep dive. And remember, keep those brains curious. Welcome back, everyone, to another deep dive. Today, we're going to be going on a journey, a fascinating journey into the world of ring theory. We're going to be exploring this idea, this relationship between indivisible sequences and descendability. And to help guide us along, we have this paper by Ivan Zelich called Indivisible Sequences and Descendability.
It's a really good paper.
Yeah, this paper is packed with really intriguing ideas and surprising results, even if you're already, familiar with ring theory. So get ready. We're going to be stretching our mathematical minds today as we unpack Zelich's work together.
I'm really excited to dive in. I think Zelich's approach is really novel and connects these seemingly disparate areas of mathematics.
Okay, so let's start at the very beginning. Zelich introduces this concept of an indivisible sequence. And it seems pretty fundamental to like his whole construction. So I guess what exactly are these sequences and why are they so important in the first place?
So an indivisible sequence, at its heart, a one indivisible sequence connects a set S to a ring R through a special map, and it's denoted as S. So more formally, it's a pair S, where S is a map from S to R.
Okay.
And the key is that this map must satisfy this specific condition. The induced linear map, S sub R sub, from RS to R needs to be universally injective.
Okay, universally injective. So that sounds pretty powerful. What does that mean in this context?
Yeah, so it means that no matter what ring you choose, let's call it T, if you tensor this linear map S sub R sub with T, the resulting map S sub R sub C sub sub id sub sub remains injective.
Oh, okay. So it's like this map S sub R sub preserves injectivity, no matter what ring you kind of throw at it. It's quite a robust property. And Zelich gives this concrete example, right? He used a polynomial ring as something about max.
Exactly. So this example is a great way to really see these sequences in action.
Okay.
So if you consider the ring of polynomials X, where K is a field, we can actually form a one indivisible sequence using this ring.
Okay.
So we set S equal to K and define S as XA for any element as in our field K. So each element of our field K gets mapped to a simple linear polynomial in S-dex.
Interesting. So each number in K gets paired with a specific polynomial. And this example, we can say that it's one indivisible because it fulfills that universal injectivity rule that we were just talking about, right?
Exactly, yeah. If you were to explicitly write out the linear map S sub Z for this polynomial example and then tensor it with another ring, you'd find that it always remains injective.
Okay.
And Zelich also points out a key feature of this one indivisible sequence. The elements of K, when mapped into next through S, they can't generate a unit ideal in S.
Okay, so the images of the elements in our sequence, in a sense, remain well-behaved within the larger ring. They don't expand to encompass the entire ring. But Zelich doesn't stop at one indivisible sequences, does he?
No, he doesn't.
He introduces something called n-indivisible sequences. What's the idea behind those?
So you can think of n-indivisible sequences as a way to stack these one indivisible sequences together.
Okay.
Formally, it's a sequence of the form sub one sub S sub one sub cell sub 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 sub, where each subisub S sub is a one indivisible sequence over the ring R.
Okay.
And the condition here is that the images of the elements in all these sequences, when combined, still can't generate a unit ideal in R.
Gotcha. So we're taking these one indivisible building blocks.
Yeah.
And we're combining them into this larger structure while maintaining that well-behaved property, ensuring that they don't generate the whole ring.
Exactly. And this idea of stacking is crucial for some of Zelich's later constructions, especially when he connects these indivisible sequences to the concept of descendability.
Okay, so let's talk about descendability. Descendability seems to be kind of like this central theme of Zelich's work. Can you give us an intuitive understanding of what this concept means in the context of ring theory?
Yeah, so descendability is all about how properties descend or transfer between rings via a special type of map called a faithfully flat ring map.
Okay.
And you can kind of think of these maps as channels for information flow between rings that preserve certain algebraic structures.
So if we have this faithfully flat map between two rings, then we can expect certain properties from the source ring to carry over to the target ring.
Precisely. Now, A ring map being descendable means that if a certain property holds in the tensor product of the target ring with itself over the source ring, then that property must also hold in the target ring itself.
Okay.
It's kind of like saying that what's true in this like expanded version of the target ring should also be true in the original target ring.
Oh, so descendability is about ensuring a kind of consistency between the original ring and its expanded version
Yeah.
via this tensor product.
Yeah.
But Zelich's paper isn't about proving that maps are descendable, is it?
His work is all about demonstrating that we can actually use these indivisible sequences to construct maps that are decidedly not descendable.
Interesting.
In other words, he's showing that there are cases where information doesn't flow as neatly as we might expect, and these indivisible sequences are the key to understanding why.
This is where things start to get interesting. So these like abstract indivisible sequences actually have the power to disrupt the expected flow of information between rings.
Mm-hmm.
But how does Zelich actually like measure this disruption? I see he's introduced something called the descendability exponent.
Yeah, that's right. The descendability exponent quantifies how descendable a ring map is. It's a numerical value. A higher exponent indicates a greater degree of descendability, so conversely, a lower exponent or even an exponent of 0 means the map is less descendable and potentially disrupting the transfer of properties between rings.
So it's like a gauge for how effectively information can flow down from that expanded version of the ring to the original ring.
Yeah.
And Zelich's work is showing that these indivisible sequences can be used to create maps with specific and sometimes very low descendability exponents.
Exactly. It's like he's found a way to engineer maps that disrupt this information flow in a controlled manner.
Yeah.
And this leads to some of his most impressive results, especially Theorem 2.4, which establishes a direct link between the size of the sets in an indivisible sequence and the non-descendability of a certain map.
Okay, so let's get into that. Let's delve into Theorem 2.4.
Yeah.
It seems to be all about the size of the sets in an indivisible sequence. Can you walk us through like the statement of the theorem and kind of like what it's really saying?
Okay, sure. So Theorem 2.4 states that if we have an n-indivisible sequence and the cardinality of each set subi sub is at least as large as subi or sum, then a particular X group, denoted as X up sub sub subn sub cocoresi sub subn and sub c, is non-zero.
Okay, hold on. We need to unpack that. Is subion sub, that's a left notation, right?
Yes.
Used to describe the size of infinite sets. So the theorem is saying that if the sets in our indivisible sequence are like sufficiently large in terms of their like infinite cardinality,
Yeah.
then this X group doesn't vanish. But what is this X group exactly, and why is it so important?
Yeah, those are good questions. So X groups, short for extension groups, are a really powerful tool in homological algebra. They help us understand how modules can be extended or built from smaller modules.
Okay.
In this context, the specific X group in Theorem 2.4 is measuring something about the relationship between the leftover parts of our ring after applying the maps in our indivisible sequence, which are represented by the co-kernels of those maps, and the free module generated by the elements in all of our sets,
Yeah.
subi sub.
So this X group is capturing some intricate algebraic relationship within our ring, a relationship that's influenced by those indivisible sequences. And the theorem says that if our sets subi sub are large enough, meaning their cardinality is at least a certain LF number, then this X group is guaranteed to be non-zero. But how does this non-vanishing X group lead to the construction of non-descendable maps? Like, it seems like kind of a jump.
Yeah, so that's the beauty of Zelich's work. He so masterfully connects these seemingly abstract concepts. He uses the fact that this particular X group is non-zero to demonstrate that a specific diagram of ring maps, which he details in Theorem 2.7, cannot exist.
Oh, okay. So the non-vanishing of the X group acts as a sort of obstruction, preventing the existence of a certain type of diagram.
Mm-hmm.
I'm starting to see how this might lead to non-descendability, but can you elaborate on how this diagram works and why its impossibility forces a map to be non-descendable?
Let's move on to Theorem 2.7.
Okay, sounds good.
So before we moved on to part 2, we were discussing that remarkable connection between indivisible sequences and the concept of descendability in ring theory, and how the non-vanishing of a particular X group could actually obstruct the existence of these specific diagrams of ring maps.
Right, and that's where Theorem 2.7 comes in, right? It kind of like it lays out a specific diagram involving these faithfully flat maps and the indivisible sequences. Can you walk us through like what this diagram looks like and how it connects to that that non-vanishing S group that we were talking about from theorem 2.4.
Yeah, so imagine we have an n-indivisible sequence, sub 1 sub, a sub 1 sub, sub 2 sub, sub sub, sub sub, sub sub, over a ring R. Theorem 2.7 introduces 3 rings for each element in our sequence. So R subi sub, a subi sub, and a subi sub.
Our subi sub, that's the free module generated by this subi sub. We saw that in the definition of the X group from theorem 2.4.
Exactly, yeah. It's playing a key role here, too. Now, these rings, a subi sub and subi sub, are connected to our subi sub through specific ring maps. So we have a map subi sub from a subi sub to our subi sub, and then a map subi sub from a subi sub to b subi sub. And the crucial detail is that subi sub is required to be faithfully flat.
Faithfully flat, there's that term again.
Yeah.
It ensures that certain properties transfer nicely through the map.
Yeah.
But how do these rings and maps kind of like fit into the larger picture?
Well, so Zelich constructs a diagram where for each eye we have this little triangle. So a subi sub at the top with subi sub going down to b subi sub on the right and g subi sub going down to the left to r subi sub.
Okay, so we had these individual like triangular diagrams,
right?
One for each element in our indivisible sequence.
Right.
What's the next step?
So then we take the tensor product over R of all of these diagrams, which essentially like glues them all together into a larger diagram.
So we're scaling up the construction, right? By combining all these individual pieces into a more complex structure.
Yeah.
What does this larger diagram look like?
So in this larger diagram, we have a map from sub a number, sub a subi sub to sub a number sub subi sub. And this is where things get really interesting. So Zelich demonstrates that because of the properties of those indivisible sequences and the non-vanishing X group from theorem 2.4, this map from sub a subi sub to sub a nun or sub subi sub cannot be descendable.
Wait, so by combining these smaller diagrams, each of which might have descendable maps, we end up with this larger map that's not descendable. That's pretty counterintuitive.
Yeah, it is, and it really highlights the power of Zelich's construction. He's essentially found a way to amplify that non-descendability by, carefully combining these individual components.
Yeah.
And that non-vanishing X group acts as a barrier, preventing the larger map from inheriting the descendability properties of its parts.
That's a brilliant insight. So the non-descendability, it's not just like this local phenomenon within like each small triangle, but it emerges from the global structure of the combined diagram, right? It's like those individual maps are almost like conspiring together to disrupt the flow of information in the larger picture.
Yeah, precisely. And this isn't just a theoretical curiosity, Zelich uses this construction to actually provide concrete examples of non-descendable maps between specific types of rings, namely sub-1 sub-Noetherian rings and Boolean rings.
Right. Those were mentioned in corollary 2.13.
Yes.
Let's dive into those examples a bit. First, can you remind us like what are A1 sub-Noetherian rings and why are they important in the first place?
Yeah. So an A-sum sub-Noetherian ring is a ring that satisfies this specific chain condition on its ideals.
Okay.
It means that any ascending chain of ideals eventually stabilizes.
So there's a limit to how much ideals in this ring can like grow. It's like a built-in control mechanism.
Right.
But how do these rings fit into Zelich's instruction of non-descendable maps?
Well, corollary 2.13 states that using this framework of indivisible sequences and the diagram from theorem 2.7, we can construct a non-descendable map between two subnull sub-Noetherian rings. Okay. And what's remarkable is that we can precisely control the descendability exponent of this map. It turns out to be exactly n.
So not only can we create these non-descendable maps, but we can even like specify how non-descendable they are by tuning this parameter n.
Yeah.
That's pretty amazing. What about the p-Boolean rings? How do they enter the picture?
So p-Boolean rings are another fascinating class of rings.
Okay.
These are rings where every element is equal to its pth power, where p is a prime number. They have these unique properties that make them important in various areas of algebra, especially when studying concepts related to fields of characteristic p.
So in these rings, the operation of raising an element to the soth power becomes like trivial.
Right.
It doesn't change the element at all, which is pretty unusual. But how does Zelich utilize these rings to construct non-descendable maps?
So corollary 2.13 also demonstrates that we can construct a non-descendable map between two Boolean rings using the same framework from theorem 2.7.
Okay.
However, there is a key difference here. In this case, we can make the descendability exponent of the map arbitrarily large.
Arbitrarily large, that means we can create maps that are like almost but not quite descendable.
Exactly.
The maps that can like transfer information for a long way before things break down. That's a pretty significant result, right?
Yeah.
It really pushes the boundaries of what we thought was possible with descendability.
Precisely. So Zelich work reveals that, descendability isn't just this simple binary concept. It's not just a matter of whether a map is descendable or not.
Right.
There's like this whole spectrum of descendability. Yeah. And we can now explore this spectrum using these indivisible sequences as our guide.
This is mind-blowing. It's like Zelich has opened up like this whole new dimension in ring theory. But before we get too carried away with with the implications of all of this, can we revisit the mechanics of how these non-descendable maps are actually constructed, like in Theorem 2.7? I'm still a bit like fuzzy on the details of that crucial diagram.
Absolutely. Like let's unpack those details a bit further. So, remember we have this diagram with those three rings for each element in our indivisible sequence. A subisub, bazibisub, and r subisub connected by those maps Q subisub and those faithfully flat maps of subisub. And the key to understanding like how non-descendability emerges is to look really closely at what happens when we take the tensor product of all these diagrams.
Okay, so let's focus on that tensor product operation.
Right.
It's clearly doing more than just like gluing the diagrams together. It's somehow creating the situation where non-descendability can arise.
Right. You're exactly right. So when we take the tensor product over R of all of these, individual diagrams, we're essentially creating this new larger ring. And it's denoted by subinyen or subasubius. This ring has a map down to another ring, sebin or subsubisub, which is constructed by tensoring together all those individual maps of these.
So we're lifting those individual maps subisub like into this new tensor product world.
Right.
What's so special about this new map between the tensor product rings?
So this new map inherits some of the properties of those individual subisub map. So in particular, since each subisub was faithfully flat, the tensor product of all of the subisubs is also faithfully flat.
Okay, so we've preserved this faithfully flat property in this larger map. But how does that lead to non-descendability?
So this is where things get a little subtle. So Zelich uses this really clever argument that hinges on the properties of those indivisible sequences and the non-vanishing X group from Theorem 2.4. He essentially shows that if this large map, the tensor product of the subisubs, were descendable, it would imply the existence of a certain homomorphism between modules.
Oh, okay. So he's using descendability to kind of like probe the existence of this particular homomorphism.
Precisely. And here's the key. That non-vanishing of that X group we talked about earlier directly contradicts the existence of this homomorphism.
So it's like that non-vanishing X group is like throwing a wrench into the works, right?
Yeah.
Preventing this homomorphism from existing.
Exactly. And that means our initial assumption that the large map between the tensor product rings was descendable must be false.
Right.
The non-vanishing X group acts as an obstruction, forcing this larger map to be non-descendable.
Wow, that's quite an intricate argument.
Yeah.
It's remarkable how Zelich weaves together these different concepts, these indivisible sequences, faithfully flat maps, tensor products, X groups, to arrive at this, kind of surprising conclusion.
It's a real testament to, his ingenuity and deep understanding of the subject.
Yeah.
And it highlights the interconnected nature of mathematical concepts. Even seemingly abstract ideas like these X groups can have these, profound implications in other areas, like the study of descendability in ring theory.
And that's why we love, diving deep into these research papers, right? They expose us to these beautiful connections and unexpected results that push the boundaries of our understanding.
I completely agree. And Zelich's work is just the beginning. His construction of these non-descendable maps raises so many questions and opens up these exciting avenues for future research.
Indeed, it's like he's given us a map, right? To this vast uncharted territory in ring theory, inviting us to explore its hidden wonders. But for now, let's take a step back and kind of like reflect on the broader significance of Zelich's findings. Like, what are the implications of this work for our understanding of ring theory and beyond? I'm eager to hear your thoughts in part 3. Welcome back to the deep dive. We've been on quite a journey so far, exploring Ivan Zelich's work on indivisible sequences and descendability, unraveling these, kind of intricate connections between these seemingly abstract concepts and how they impact the world of ring theory.
Yeah, it has been fascinating. We've gone from the basic definition of indivisible sequences all the way to their role in constructing maps that really defy our expectations about how properties should transfer between rings.
And we even delved into the mechanics of those constructions, right? Seeing how, Zelich leverages faithfully flat maps, tensor products, even, X groups to create those non-descendable maps. But now I'm curious, about the broader implications of this work. What does it all mean for our understanding of, of ring theory and beyond?
Yeah, so I think Zelich's work has, several significant implications. First, it provides us with this powerful new toolkit for constructing examples of non-descendable maps.
Right. Before his work, finding these kinds of examples was often a really difficult ad hoc process.
Exactly. It relied on specific properties of, particular rings or these clever tricks that didn't really generalize well.
Right.
Zelich's approach, using indivisible sequences in homological algebra is much more systematic and broadly applicable.
Yeah, and that opens up this whole new avenue for exploring descendability.
Yeah.
Right. We can now construct a wide variety of non-descendable maps with different descendability exponents between various types of rings. And that allows us to study descendability as this more nuanced concept.
Yeah, it's no longer just a yes or no question of whether a map is, descendable. We can actually fine-tune the level of descendability, creating a spectrum of possibilities to investigate.
Yeah, that's a profound shift in perspective.
Absolutely, and it has the potential to shed new light on these fundamental questions about, ring extensions and how properties transfer between rings. For example, we might ask, what are the necessary and sufficient conditions for a map to have a specific descendability exponent? Or, how does the descendability of a map relate to other important properties of the rings involved?
Right. Those are great questions. It seems like Zelich has given us this new lens through which to view this whole concept of descendability, revealing this depth and complexity that we hadn't fully appreciated before. And his work, it goes beyond just providing new tools and perspectives, right?
Yeah.
It's also challenging some of our assumptions about how information should flow between rings.
Yeah, you're right. His construction of these non-descendable maps demonstrates that information transfer isn't always as straightforward as we might think.
Yeah.
There are these subtle obstructions, like that non-vanishing X group we discussed, that can disrupt the expected flow of properties.
Because those faithfully flat maps, which we usually think of as these reliable messengers, can sometimes hit these unexpected roadblocks, right?
Right.
Preventing certain information from reaching its destination.
Right.
And those roadblocks are encoded in the structure of those indivisible sequences.
Precisely.
Yeah.
It's a really fascinating interplay between these different algebraic structures, and it highlights the importance of, carefully considering the context when we talk about properties transferring between rings.
Yeah. Another aspect that I find really intriguing is how Zelich's work connects these seemingly disparate areas of mathematics. Who would have thought that these abstract indivisible sequences would have such profound implications for the study of descendability?
It's a beautiful example of, the interconnectedness of mathematical concepts. Ideas from set theory, ring theory, homological algebra, it all comes together in his work, demonstrating that even the most abstract concepts can have these really surprising applications in other areas.
And that interconnectedness is what makes mathematics so captivating. Right? It's like exploring this vast, intricate web of ideas where each discovery illuminates not only its immediate surroundings but also these distant, seemingly unrelated parts of the web.
Exactly. And Zelich's work is just one thread in that web, but it's a thread that has the potential to lead us to even deeper and more profound discoveries.
He hints at this in the paper, right?
Yeah.
Suggesting that similar constructions might be applicable in other algebraic settings, beyond just ring theory.
Yeah.
That's a pretty exciting prospect.
Yeah, it would be fascinating to see if if his techniques could be adapted to study, descendability in other contexts, like module theory or representation theory, it could open up, whole new areas of research and lead to a deeper understanding of how algebraic structures interact.
It's a real testament to the power of mathematical inquiry. Even the most abstract ideas can have these far-reaching consequences, shaping our understanding of the world around us in ways that we might never have imagined.
Absolutely, and that's why we keep diving deep into these research papers. They're not just these dry technical documents. They're windows into a world of wonder where beauty and complexity intertwine, revealing these hidden patterns and connections that govern the universe.
Well said. Well said. And big thanks to Evan Zelich for providing us with such a thought-provoking and insightful paper. It's been a real privilege to unpack his work and explore the depths of its implications.
Couldn't agree more. And thanks to all of our listeners for joining us on this deep dive. We hope you found it as enlightening and engaging as we did.
Until next time, keep exploring, keep questioning, and keep diving deep.